Good morning, guys. Today we're going to look at solving linear systems using Cramer's rule. It's another technique using matrices, but we're going to focus more on the determinants this time. So first part of Cramer's rule, as you can see, is I want to identify my coefficient matrix and my constant matrix. I always think it's very important on this. Again, with matrices, lots of numbers in there, lots of small calculations. Being organized is key. So I like to label my X column, my Y column, and I'll put a K for the constant column. In math, sometimes we make constants K because we use C for so much other stuff. So X column, Y column, constant column. The good thing about Cramer's rule is after a couple of quick determinants, I have the answer. I'm not having to figure out determinants and then do all these calculations and substitute numbers and all that stuff. It takes me straight to the answer. It says X equals this fraction. This determinant divided by this determinant is what X is equal to. This determinant divided by that determinant is what Y is equal to. If I had a three-variable system, the determinant of the numerator and denominator for that third variable for Z would tell me what Z is equal to. So it jumps you straight to the answer. You just have to remember the setup. Now, setup has a pattern to it, has a system to it. So let's look at what that is. And remember, labeling these columns will make it a lot easier to remember this. Denominators are always the coefficient matrix. X column and Y column. X column and Y column. Order is very important. X's, then Y's, because that's how we have the constants set up. X was our first one. Sorry, first equation, second equation. We'll have X is first, Y is second. So be consistent with that. For the numerators, you're going to take your coefficient matrix and you're going to replace what you're solving for with the constant matrix. So where we have xy in our denominator, instead of the numerator being xy, since we're solving for x, we're going to replace the x column with the constant column. So x is being solved for, so x gets replaced. Note the position of y. Y is still on the right-hand side. We didn't move the y over and slide the k in. X was the first column, so we put the constants in that first column. Y stayed the same. For our y value, constant matrix or coefficient matrix is in the denominator. So we take our coefficient matrix for the numerator, but since we're solving for y, we replace that y column with our constants. Calculate these quick determinants, do your fraction, and you will have your solution. Give me a second, and I'll get a couple examples up for you guys. So let's look at our first example here. We want to use Cramer's rule to solve this two-variable system. Now, to start out, we need to identify the coefficient matrix and the constant matrix. So that's what I will start with. Coefficient matrix. 2 and 1 are my x's. 7 and 3 are my y's. Let's get a better marker. Constant matrix. Negative 53 and negative 22. I want to go ahead and label them. X column, Y column, constant column. And then we just set up Cramer's rule. Cramer's rule tells us to get the X value, it's going to be a fraction. Denominator is the determinant of the coefficients, 2, 7, 1, 3. Numerator, since I'm solving for x, instead of it being xy, I replace the x and leave the y. Replace what you're solving for. So the y's are still 7, 3. The constants are negative 53 and negative 22. Let's go through and do the math. Negative 159. We'll say negative 154. So minus negative 154 equals negative 5. Right here, 6 minus 7 is negative 1. So x equals 5. So by a couple of quick determinants, we know that the x coordinate is 5. Well, let's look at the y coordinate now. Y is equal to determinant of the denominator, determinant of the coefficient matrix is our denominator. So xy, so that's still going to be 2, 7, 1, 3. And the good thing is, once you do one denominator, you're finished with all denominators because it's the same in every single one of them. So we already know that I'm going to get -1 for that bottom. So as long as you know you've calculated your first one correctly, the rest of them you don't have to worry about any denominators. So it may look like a lot of determinants you're calculating, but in this specific one we're just doing 3 determinants, so we've already knocked one of them out. For the numerator, solving for y, so I replace y. Not quite big enough. So instead of it being xy, it becomes xk. Take the time, be organized, and label. So my x's are still 2, 1. My k's are -53 and -22. Do your determinants. -44 minus -53 minus negative gives us +9 over -1, so -9. X equals 5, y equals -9. There's the solution to our system. As you can see, we have problem number 2 up here on the board. 3 variable system, but the process is the same. Whatever I'm solving for, I replace that column in the numerator with my constants, and my denominator is always my coefficient, or the determinant of the coefficient matrix. Pause the video, take a couple minutes, and try to calculate, try to solve that linear system using Cramer's rule. And I'll wait right here. Alright, so hopefully you've got the solutions. Let's go and check your work. As you can see, I've already kind of set it up. In general, x's, I've got my coefficient matrix. Coefficient matrix is my denominator. In each case, a lot of numbers there. Make sure you've got them in the right order, in the right places, with all your negatives included. Got my constant matrix, and we're going to fill that in right now. So in x, my constant matrix will go in the x column. -4, 1, -5. In y, my constant matrix will go in the numerator of the y column. -5. Lose a negative sign, it throws everything off, so be very careful. And in z, numerator z column. Alright, so it is a lot of numbers, but let's go through and try to do these determinants. I'm going to do diagonal method on these 3x3s just because I don't have a lot of space. I think I can do that kind of compactly. So repeat first 2 columns, -4, 1, 1, 2, -5, -1. -4, 2, 1 is -8. 1, 4, -5 is -20. 6, 1, -1 is -6. Minus 1, 1, 1 is 1. Minus -4, 4, -1 is 16. Minus 6, 2, -5 is -60. Do that arithmetic right there. And we get plus here. Minus there, minus there, minus there. Okay, so we're going to get -28, -34, -35, -35 and 16, -51, -51 and 60 is 9. Okay, first numerator done. Let's do this denominator. Remember, once I get this denominator calculated, I can go ahead and throw it in all my other denominators. But let's go. Rewrite first 2 columns. 4, 1, 2, 2, -1, -1. 4, 2, 1 is 8. Plus 1, 4, -1 is -4. Plus 6, 2, -1 is -12. Now coming back the other way. Minus 1, 2, 1 is 2. Minus 4, 4, negative 1 is negative 16. Minus 6, 2, negative 1 is negative 12. That becomes a plus, becomes a plus, becomes a minus, becomes a minus. Okay, so I've got 8 and 12 is 20, 36, 36, 4 and 2 is 6. 6 and 12 is 18, so 36 minus 18 is 18. 9 over 18 is a half. Okay, so we get a half for our x value. I can go ahead and throw 18 into my other denominators because they're the same for all of them. So all of them have the same denominator, so I'm finished with them. We just have these last two numerators and we've solved the system. I go through, let's do this, the y numerator. 4, negative 4, 2, 1, negative 1, negative 5. 4, 1, 1 is 4, plus negative 4, 4, negative 1 is 16, plus 6, 2, negative 5 is negative 60, minus negative 4, 2, 1 is negative 8, minus, 4, 2, 1, 4, 4, 5. 4, 4, negative 5 is going to give me, I can't even think right now, negative 80, minus 6, 1, negative 1 is negative 6. That'll become a plus, that'll become a plus, that'll become a plus, that'll be a minus. So we combine all that together, we know it's going to be over 18, 20, 100, 100 and, well, I can't even think right now, 114 minus 60 is 54. And 54 over 18 is 3. So y value is 3. For z, let's go through and do it. Move these guys. Rewrite first two. 4, 1, 2, 2, negative 1, negative 1. 4, 2, negative 5 is negative 40. Plus 1, 1, negative 1 is negative 1. Plus negative 4, 2, negative 1 is 8. Minus the right-handed ones. 1, 2, negative 5 is negative 10. Minus 4, 1, negative 1 is negative 4. Minus negative 4, 2, negative 1 is positive 8. That'll become a plus. That'll become a plus. That'll be a minus. Negative 41, negative 49, negative 39, negative 31, and negative 27. Negative 27 over 18 gives us negative 3 halves. So, by doing a couple of quick determinants, we did 4 determinants, and we've solved this system to get the ordered triple of 1/2, 3, and negative 3 halves. Now you may be sitting there, why would I go through all that when I could have done linear combination with those, when I could have done a substitution with those? Maybe this is the best way if these numbers are really, really nasty. I mean, if you're comfortable with it, the actual calculation process takes about 4 minutes to do. So once you get it set up, you know, you got about 4 minutes worth of calculations to get your system solved. Where this is better than some of the options like inverse matrices, for example. Inverse matrices, you have to have the inverse. Well, the inverse of that coefficient matrix, which is 3 by 3, is a beast to do by hand. It's very, very nasty. And doing these 4 determinants is a lot faster if you've got a 3-variable system than trying to use something like inverse matrices. If you like Gauss-Jordan elimination, you know, it's probably just as fast as this. But this is just another technique that you can use. Really good with 2-variable systems because the determinants are so quick to calculate. But if you've got to do a 3-variable system by hand, that's one where you know how to calculate these determinants. And sometimes you get ones with, you know, a lot of ones in there and they can go a lot faster. If I had a little more room, I probably would have done expansion by minors, and it would have sped the process up a little bit, but I just wanted to keep it organized where we could see. All right, one example I want to pull up here before we go, and let's look at Cramer's rule on this system right here. So let's say we have the system 2x minus 4y equals 9, 3x minus 6y equals 6. Okay? So I've got this system sitting right here. We're going to do Cramer's rule on it. X equals 2, negative 4, 3, negative 6. Solve for x, replace x. So 9, 6 in the x column. Negative 4, negative 6 stays in the y column. For y, we know we're going to get 2, negative 4, 3, negative 6. We know we're going to get solve for y, so we replace y. So 9, 6 in the y's, and then the x's stay the same. Go through and do our quick determinants. For the numerator, I get negative 54. Right here, I get minus negative 24. Brain's a little fried on my arithmetic after that last one. Add them up, so you get negative 30. Here I get negative 12 minus a negative 12. Add those up, and you get 0. So I get 0 for this one also, I guess, for the denominator. So, can't divide by 0, so that's undefined. And that kind of goes to where we had talked earlier when we were doing determinants. A 0 determinant, or a determinant, can tell us a whole lot about a system just by knowing its value. If that value is 0, we obviously can't get a solution in that case. Now, as we can see in this case right here, 2 to 4, 3 to 6, that's a 1 to 2 ratio, right? So that's telling us that since they both have a 1 to 2 ratio, the slopes are going to be 1/2. Okay, the slopes are going to be 1/2 or negative 1/2, just depending on, this one would be 1/2 because you'd subtract your 2 and divide by negative 4. Subtract your 3, divide by negative 6. So you'd get a 1/2 for your slope. Y-intercepts, however, this one would be negative 9/4. This one will be negative 1. Same slope, different y-intercept is a no solution system. So when we get that 0 for that determinant off the coefficient matrix, we know right now we've got either a no solution or infinitely many solution system. We go back and do a little inspection of the original system. If you need to put them into slope-intercept form to compare slopes and y-intercepts, go ahead and do it. But do a little inspection. See whether it's infinitely many solution, same slope, same y-intercepts, or no solution system, same slope, different y-intercepts. Now I'm going to tell you this is going to happen and will also help you if you remember it. If your numerator also gives you 0, while the denominator gives you 0, that will be your infinitely many solutions. Say we had this right here. 6 and 9 right there. So if I'd have flipped my 6 and my 9, okay, 4 into 6 is 3/2, 6 into 9 is 3/2, so we get infinitely many because the slopes and y-intercepts are now matching up. The numerator's determinant now, 6 and 6 is negative 36, negative 4 and 9 is negative 36. Change that to addition, gives us a 0. So if the denominator gives you 0, along with the numerator, think of it as like a 0 equals 0 like we had when we were solving systems algebraically, infinitely many solutions. But if it's another number like we had a second ago, that 30 over 0, number over 0 is going to be your no solution systems. If you can remember that, it's good. It'll save you a little time. If you don't, a little inspection of the original system will tell you whether it's no solution or infinitely many solutions. So, that's solving linear systems using Cramer's rule. Good technique if you've got a 3-variable system and don't want to calculate the inverse by hand and don't want to go through all your elementary row operations from Gauss-Jordan elimination. Or if you just want to do a quick jump to the answer for a two-variable system, Cramer's rule is a really good technique to use. That's systems linear equations with Cramer's rule, and I will see you in class tomorrow, guys.